Hi, Chem 240. This is Dr. Ricardo. We're going to start the videos for Chapter 14. My estimation is that we should be able to do this in either 3 videos or 4 videos of an hour each. Chapter 14 is on the rates of reaction, also called chemical kinetics. So this is the first and only time in general chemistry, and honestly, in most chemistry courses that you're going to take, where you're actually going to discuss how fast a chemical reaction occurs as opposed to how much of a material you make, okay? Most of our focus in general chemistry is on the thermodynamic aspects, right? What is the heat associated with a chemical reaction? What is the quantity of material you can make? All of those have to do with stability. All of those have to do with energy. Energy only interfaces with speed in a few different places. So first we'll go through chemical kinetics, the idea of tracking how fast chemical reactions take to occur, and then we'll connect it back to thermodynamics in one particular place, okay? All right, so some definitions. Reaction rates and chemical kinetics. So chemical kinetics is the study of how fast chemical reactions occur, okay? These are the factors. I have A, B, C, and then 4. I guess this really should be changed to D down here, okay? So what are the factors that affect how fast a chemical reaction takes place? Well, the first thing that's critical is the concentration of the reactants in the solution. Whether you're talking about a gas phase reaction or a solution phase reaction or a liquid phase reaction, the individual molecules that are going to react have to meet up with one another. So they're much more likely to meet up with one another and collide and go on to undergo fruitful reactions if the concentration is high. Okay? So the second factor is temperature. The higher the temperature, the faster the particles move. The faster the particles move, the more likely they are to come into contact with one another. So that's the first reason why temperature is important. The second reason why temperature is important is because the faster the molecules move, the more kinetic energy they have, the harder the impacts between them. And if the impacts are harder, the more likely that old bonds will be broken and new bonds will be formed. Okay, so 2 cars hit one another on the road going very slowly, then they'll probably have a elastic collision. They'll probably hit into one another and bounce off with no damage done. But if the 2 cars hit especially hard, they can actually cause damage to one another. And in a sense, a chemical reaction is damage because we want to break some of the old bonds and replace them with some of the new bonds. So faster and harder come from higher temperature. Okay, molecules are moving faster. If they're moving faster, they're going to hit each other harder. Third thing is the presence of a catalyst. When you add a catalyst to a chemical reaction, you actually change the mechanism in which the chemical reaction occurs. Instead of going over maybe a very hard pathway that involves some very steep energy barriers, you change the scenario totally and you go a different way. You still arrive at the same final destination of products, but they may occur through a much easier pathway. You could look at it like building a bridge across a river is a catalyst. You're standing on one side of the river in New York, and you want to get to the other side. Well, you can swim across, you can take a boat across, or you can go over the bridge. The bridge is a catalyst. You still wind up in New Jersey, but this time you took the easier pathway, the pathway that isn't less or more energy because you wind up in the same place. What it is, though, is faster. Okay, so that's the first 3 things. And D, the 4th thing, is the surface area of any solid reactants or catalysts. Okay, anytime you have a solid involved in the chemical reaction, the only place where the reaction can occur is on the surface. So if you grind up the material and have it in very, very finely divided powder, then that's much more surface area than you have just in one big block of steel. So if steel isn't such a good example, let's say iron. Let's say iron is the particular chemical catalyst, okay, or the chemical reactant. If I grind it up into smaller pieces, okay, if I grind it up into smaller pieces, those pieces will react faster because the reaction has to take place on the surface. And the more surface area, the more likely it is to occur. Okay? Think about the difference between making a cheeseburger with a slice of cheese or using grated cheese, right? Grated cheese, like when you, on your tacos, okay? When you take that and you put that onto the top of your cheeseburger, you'll see it'll melt faster because there's much more surface area. Okay, so a lot of our melted things like tacos and nachos, we tend to use grated cheese. The larger the surface area, the faster the chemical reaction. Okay, here's the definition of a catalyst. A catalyst is a substance that increases the rate of a reaction without being consumed in the overall reaction. In this scheme here, A and B are chemical reactants. Okay, that particular reaction can maybe take place to form C without extra hydrogen ions, right? So this is called an acid catalyzed reaction because you know from Chem 1 that H plus is the active ingredient that comes from an acid, right? H plus or H3O plus. So in the presence of the H plus, the A and B can react to form C much faster. Why do we write the catalyst on the top of the line as opposed to as a reactant? Because not only does it go into the chemical reaction, it also comes back out the other side. So you need it in order for the chemical reaction to occur faster, but it's not a reactant or a product. So another way I could write that is I could write that as A plus B plus H plus goes to C plus H plus, right? So look, H plus was needed for the chemical reaction, but it was also reproduced, so I don't use any of it up. So if I was writing the net ionic reaction for this, or the net reaction, if I have the same thing with the same coefficient on both sides, they would cancel out. So how better could we write that? By just putting it on the top of the line. You need the H plus for the reaction to occur at a reasonable rate, okay? You don't want to take forever for something to happen. So this would be the case of a chemical reaction that was acid catalyzed. A lot of this in cooking. A lot of times we add lemon juice, right? The function of lemon juice is to make something a little bit more acidic. Well, you can catalyze the cooking process with the lemon juice. Okay. All right. Next thing we need to talk about is the reaction rate. Okay, so we're going to quantify how fast a chemical reaction occurs, okay, by discussing its reaction rate. So the reaction rate has the following properties. A, it's an increase in the molar concentration of the product in reaction units, reaction per unit time. So the denominator is always going to have the change in time. So you start the stopwatch at the beginning of mixing A and B together, and you stop the stopwatch, okay? You stop the stopwatch at a given time after the reaction occurs, and you check out how much C was produced. So we could follow this chemical reaction here by following the change in concentration, like the brackets mean concentration in moles per liter, right? So that's very important. Anytime you see this, whatever's in there, you're talking about that substance's concentration in molarity, which is moles of X per liter of solution. That's our most important concentration unit. Last chapter in 13, we learned about molality. Honestly, we're not going to use it very much anymore. The only time you use molality is for the colligative properties. Okay, so anytime you see brackets, it means the concentration of that substance in moles per liter, molarity. All right, that's the big one, capital M, not fancy script M. Okay, so again, you have a choice. You can watch A or B disappear, or you can watch C appear. If I was graphing this, and I was following the concentration of C, how many moles per liter of C I have at any given time, and this is time 0, and this is time, let's make it 10 minutes. Okay, so this is time. So I'm following C grow in. Well, in the beginning, there isn't any C because A and B didn't react. All of a sudden, I mix A and B and start the watch. Well, what's going to happen is the concentration of C is going to go up. okay? And then eventually it'll start to tail off, okay? And it'll go up slower until it reaches a final concentration. But initially, out of the block, it actually would start at 0, okay? And go up very quickly and then tail off. So we would be following the change in concentration over time. So if I asked you from 0 to 5 minutes, you could look at the average change by taking the change in the concentration, this value, minus this value, which is 0, divided by the x-axis here. So the denominator would be 5 minutes, the numerator would be whatever this difference was. Okay? Since we're starting at 0 here, this would be the concentration of C. Okay, so what we would be doing is following the growth of one of the products with time. Okay, so that's the first thing that you can study. Notice, this guy has a positive sign on it because it's a product. It's growing in. This is a one-way arrow. The reactants are going to react to create C. So the reaction rate can be measured by following the positive change in the concentration of the product with time. Or it can equally be represented by watching one of the reactants decrease. A decrease in the molar concentration of a reactant per unit time. So I could equally follow the concentration by watching the negative change of concentration of A with time, right? I could do this also with B. So I'll write that down in a second. Okay, so remember, here's our chemical reaction. A or B are reactants. So I could equally follow A and watch it disappear. Now remember, if I was following the concentration of A with time, A has to start at some finite amount. Why? Because it's a reactant. I have to have some of it around, so I know the initial amount of A in the solution before I put it into B, before I put B in. So this is at time is equal to 0, and the initial concentration is equal to A, okay? Mix it with B. Start the stopwatch. What's going to have to happen to it? It's got to go down. Why does it have to go down? Because I'm using it up, right? It's a chemical reactant. It has a certain value. As it reacts with B, it disappears. So the concentration of reactants drop. Hey, in the beginning, it's going to drop very fast, but then it'll level off for a reason, and then ultimately I could potentially use it all up. So the graph would look like that. B would do the same thing. Why would B do the same thing? Because it's also a reactant. So I'm going to always have a choice. What do I want to follow? Do I want to watch the reactants disappear with time, or watch the products grow in with time? Here's the product growing in with time, okay?
Unknown caller.
Hold on one second. I'll